Hi, everyone. So welcome to our session today. We're going to be studying A-level physics, and in particular, we're going to be studying stationary waves. Okay, so this is a really nice topic. I'm really looking forward to going through this. We'll give people a couple of minutes to filter in. And in the meantime, I'll just mention a bit about how the session is going to work. So first of all, I have my eye on the chat section on the YouTube live stream. So if you have any questions about anything I've said, feel free to put your question in there. I will be keeping my eye on it. And if I can answer your question, then I absolutely will. I'm also might ask questions as I'm going through things to see if people are understanding what I'm saying and so on. So sometimes I might ask a question. Feel free to pop your best guess at an answer in the chat. No worries if you get it right or wrong. It just helps me to see how the class is going. What else? Right. So as usual, the session is going to be split into two halves. In each half, we'll learn some stuff and then do a couple of practice questions. I think that's the main stuff we're going to need to know. So I think we'll just go straight in. So like I said, as I'm going through this, if anyone has any questions, just type them in the chat and I'll keep my eye on that. Okay, good. So what is today about? Today is about stationary waves. So just to let you know a little more about SnapRevise and about me. So I'm the lead physics teacher here at SnapRevise. My name is Matt. I am or was a physics PhD student at the University of Oxford and a physics tutor for around the last 7 years or so. Okay, good. So that's me. And now this is coming from the SnapRevise YouTube channel, and more broadly, this is coming from SnapRevise. And just to let you know, aside from all the great things that we do on the SnapRevise website to help you prepare for GCSE and A-level exams, we do have something very specific coming up. So we have the A-level exam crash courses coming up. They're for biology, chemistry, physics, and maths. And they are, as the title suggests, they're crash courses to try and get ready for the exams. Each one of these, I believe, is 2 days. 1 day for AS and a separate day for A level, so you can choose which one is most suitable. And we take a lot of effort into focusing on exam technique and extracting exactly what it is that an examiner might be asking us for in an exam question. Because I know it's quite common to feel like you actually know all the stuff in the course, but when you get in the exam, you don't know what the examiner is actually asking you for. So alongside that, we tend to try and focus on the trickier topics. There will be revision booklets that you can fill in throughout the day and take home. And there will be messenger services so that you can, just as you have the chat here to ask me questions on the fly, on the day there will be somebody dedicated just to answering questions in the chat as you go through. Okay, good. So let's get stuck into the course then, shall we? So as I said, today is about stationary waves. And our goals are to understand the concepts of phase and superposition. We'll need these if we're going to understand stationary waves. We're going to try and describe then how stationary waves are formed. And we're going to define the nodes and harmonics of a stationary wave. Things we won't be covering are interference patterns of stationary waves in air columns. Good. Okay, so as usual, before we get started, it's a good idea if we can just revise a couple of topics that will be handy to know today. And today, the main thing is to know some terminology about waves. So, okay, I'm going to point to a couple of bits of this intuitive picture of a wave that we're looking at here. I'm going to draw a line in the middle, and we'll come back to this line later. Actually, we're going to give that a name. That's one of the less common things to name, so we won't start with that. Let's say from this middle, this point where the wave would be if it kind of wasn't wiggling, from this point all the way up to the highest point of the wave, can anyone tell me what that distance or what that interval is called? The highest point that the wave can reach is one way of saying it. Another way of thinking about it is it's a bit like the size of a wave, and the technical word here is amplitude. Amplitude. Good. Yeah, really good. Amplitude. Ah, I see crest as well. So good. So the name of the interval is the amplitude, and it's often given the symbol A. And the actual point at the top is often called the crest, or also it might be called the kind of peak. There's lots of names for that point at the top. Okay, let's imagine that this axis that we have going along the page is an axis of distance. So it's like we've taken a photograph of a wave. Okay. Then in that case, what would I call the following distance? Assuming that what I just drawn was a straight line, which it absolutely wasn't. What do I call this distance? The distance between two peaks. Good, absolutely right. It's called lambda, and it denotes the wavelength. Perfect. Good stuff. Okay. If instead in fact, let's write distance in green. If instead this axis had been time, then this interval here would instead have represented the period of the wave given by the symbol t. So you have to keep an eye on that axis. If the axis is distance, it's going to be wavelength. If the axis is time, it's going to be time period. Okay, good. In general, we may look at a point on a wave and refer to this distance here for that point on the wave as its displacement, and often we'll call it x. So it's displacement. Good. And I think the only other things I want to mention is that the interesting thing about waves is they let you transfer energy without transferring matter. So let's say I wanted to knock an object over on the other side of the room. One thing I could do is take what's in my hand, in this case it's a set of keys, and I could launch the keys at the object, hoping to knock it over. That would be transferring energy, but it would be doing it by transferring matter. The keys would have to leave my hand and go reach the thing that I want to transfer energy to. On the other hand, I could fire a high-powered laser or something like that at the object. And then I wouldn't really be transferring any mass across the room, but I would be using a wave to get energy to the other side of the room instead. So waves are interesting because you can transfer energy with them without having to actually launch mass somewhere. Okay. What else do I want to say? Oh yeah, just one more thing. There's this quantity called the frequency. Is essentially the number of times that a wave is oscillating per second. And formally, as an equation, it's always 1 over the period. So it's actually this. Good. I think that's all we need to say there. So let's go ahead. Just for a bit of reference, here are the spec points that we're going to be going through for the 3 main exam boards. So that was AQA. This one is OCR. And then this one is EdXL. Okay, very good. Right, so let's get started with the first half of our session, and we're going to talk about the formation of stationary waves. And as I said at the beginning of the session, to even get there, we're going to need to settle some terminology. So first of all, we're going to understand the concept of phase. So phase is, to some extent, just a number. For us, it's going to be a number that we use to describe a certain property of a point along a wave. So we have a wave. Here's our wave. And there's many points. There's this point, there's this point, there's this point. Each of these points will have a property called its phase, and the phase will be different in general for each of these points. So, fine. What exactly is the phase? Well, the phase of a point is there to describe precisely where that point is in its oscillation. So, for instance, let me draw another one here. This point here is at the top of its oscillation. So it's at a different phase to this point here, which is at the bottom of its oscillation. Okay, good. Now, often we care about 2 different points. So for instance, I was already doing it here. I was comparing 2 different points. And I could see that they were somehow different because there was some difference in their phase. Okay, so the phase difference expresses this, is a way to talk about the difference between where 2 points are in their oscillations. There we go, a bit of a word soup. Okay, so the phase difference between 2 points is the difference between their phases. And at this point, I might be thinking, well, we haven't actually given any numbers yet. Why do 2 points in adjacent segments are an antiphase? So we will come to antiphase in a second. So I'll mention antiphase in a second and let me know if what I've said still hasn't answered your question. Okay, so let's actually do something super explicit now because I haven't given any numbers to anything yet. So typically, we will say that the point at which an object is just about to begin its oscillation, that's a phase of 0. Now, typically, we choose for one complete oscillation to mean reaching a phase of either 360 degrees or 2 pi radians. So you can choose whether you want to measure things in radians or in degrees. The idea is that going all the way up and down like this and back to the start, we want to think about it like going all the way around a circle, which would be 360 degrees. It's a very natural analogy, and that's why we choose these units. Okay. So given that, what phase should we assign to this point here in between? At the beginning, we're at 0. At the end, we're at 360. What's this phase here? (180 degrees. Absolutely right. Good. Similarly, this is 90 degrees. And this is 270 degrees. Also note that 90 degrees, that's the same as pi over 2 radians. This is the same as pi radians. This is the same as 3 pi over 2 radians. So, okay, in terms of overtones, I will remember your question. We're going to actually be talking about harmonics in the second half of this session. So it'll be more natural to touch on them at what I can actually remember about them then, if that's okay. But we will come back to them. Okay, so yeah, finally, when one point is let's say, yeah, just to talk quickly about antiphase, since it came up. When 2 points are both kind of at the same point in their cycle, albeit by a difference of, say, 360 degrees, then we could say that they are in phase. So for instance, this point here, this point 1, and this point here, let's call it point 2, these points are in phase because they're both at the same point in their cycle, plus or minus 360 degrees. It's just one whole cycle onwards. On the other hand, this point here is in what we would call antiphase with point 1, because it is as far down as this first wave is upwards. In other words, they're at totally opposite points in their cycle. And if they were in the same place, they would cancel each other out. And that's something we'll come back to more in a second. Okay, and so we already touched on this, but if 2 points are at the same point in their oscillation, then we say that their phase difference is approximately 2 pi n radians, or equivalently 360 degrees. Okay, good. Right. So far we've been talking about a single wave. One of the reasons why we care about phase, though, is because of what it allows us to talk about when we have 2 or more waves interacting. So we have a rule called the superposition. And the superposition rule says the following. When 2 different waves meet together, the resultant displacement, because each one is trying to make its own displacement, The resultant displacement will be the vector sum of their displacements. Of their displacements. Okay, what does this mean? Well, sum just means you add them together, no problem there. But vector sum means you have to keep account of whether they're pointing upwards or downwards. So, for instance, let's say I have this wave here on the left, which has, say, an amplitude of, let's say, x1. Let's say we have this wave here, which has an amplitude of x2. And let's say that they're traveling into each other. So at some point in the middle, they're going to meet. When they meet, this rule says we should sum their displacements. So when they meet in the middle, we'll get a new wave whose displacement is x1 plus x2. Okay. Now, from now on, we're going to assume that x1 is bigger than x2, okay? So that this thing is further up, and then this time we have a downwards wave here, x2, but it's not pointing quite as far down as x1 is pointing up. Okay. Now, the first thing that we learned here is that when two peaks or troughs meet, then the result will be the sum of amplitudes. Well, we haven't bothered to say vector anymore because both are pointing in the same direction. So it's just doing a normal addition. However, this time we're going to look at the case where a peak meets a trough. And that's where this vector word is going to become more and more important. Okay. So if we look at these two waves here, the vector sum means that if one is up and the other is pointing down, we're going to actually need to look at their difference. So assuming x1 is bigger than x2, we'll have something that just goes a little bit up. And what will the amplitude of this wave be when they meet in the middle? Okay, so the point is, in this case, the result will be the difference in amplitudes. So looking at this explicit example here, well, we have x1, which is bigger, but then we take away the influence of x2 to get this smaller thing, x1 minus x2, this little interval here. Okay, good. Sometimes this first type of combination of waves is called a constructive combination or constructive interference. And the second is called destructive. Good. Constructive because they work together to make something bigger. Destructive because they work against each other to make something less. Good. Okay. So now we've talked about how to combine waves together. Now we're going to combine this with some of our understanding concerning phase. And we're going to talk about stationary waves. So when we're talking about stationary waves, we're talking about what we really had in the last slide. We have two waves going in opposite directions towards each other. Except this time, we're going to look at a very special kind of pair of waves moving towards each other. They're going to be the same in quite important ways. They're going to be continuous. So what does continuous mean? Well, in the previous slide, we were looking at something that just looked like a pulse, a lump that was moving. Continuous means it wiggles forever, like a sine wave, for instance. Okay. Coherent means that both of these waves are going to have the same wavelength. Okay, we've got two waves. One is going to be moving, say, to the right. We're going to have this other wave. I'll draw it here, completely different colors to what's below, but it's no big deal. We have this other wave. Oh, I drew that terribly. My mouse slipped, but that's okay, in the other direction. And the point is that both should have the same wavelength and the same frequency. Okay. So it's a very special case of two waves moving in opposite directions, interacting with each other. When we have this situation, we find that we get very, very special behavior. In particular, there will be points where the waves are always in phase or antiphase. Okay, so let's take a look at our diagram and see if we agree with this statement. So there will be points where the waves are always in phase. Okay, let's find one. And a classic one would be, for instance, this one here. Okay, I'm going to use a different color because that's super hard to see. Okay, there we go. So here's a point, essentially this line here, where no matter what time we're at this point here, let's say this point here, these waves are always going to be in phase. Okay, why is that? Well, let's assume that the pink wave, do I have a pink? Let's assume that the pink wave is moving to the, let's say to the right, like this. And let's say the orange wave is moving to the left. Okay, so the orange wave is moving like this. Okay, and they're moving at the same speed because they have the same wavelength and the same frequency. Now, as they move, imagine what's going to happen to both of these waves. As viewed from this point here, this point that we're focusing on, we'll see that the orange, because the whole orange wave moves to the left, the height of the orange wave at this point is going to go down a little bit. Fine. But the pink wave is moving to the right, and you can see that as the whole pink wave moves to the right, the pink wave at this point is also going to move down a little bit. So both are going to move down. So both waves are still going to be at the same point in their cycle. They're both still going to be working together. Okay. If you imagine they'd gone in the other direction, the peaks would have matched. Fine. Now let's find a point where the waves are working against each other and convince ourselves that they will always work against each other at that point. Okay, so these ones are slightly harder to draw, but we should be able to do it. I would say something like this. Yes, good. So roughly speaking, you should be able to see that at this point in the wave, this orange line is as far up as this pink line is down. So at this point, the waves are working again. And what will the total displacement be at this point? That's a good question. What will the total displacement for the combined wave here? So one is pointing as far up as the other one is pointing down. These points are in antiphase and the displacement is going to be zero. So here, the resulting displacement is going to be zero. Let's imagine what happens a bit of time later. So the pink wave will move to the right. So in fact, you can imagine the point at which the, at which the pink wave, it actually moves so far to the right that its peak is at this point here now. Fine. The orange wave is moving the other direction. The orange has moved to the left. And if the orange wave moves to the left, its peak is going to end up here now as well. So even at a later time, they're still going to be perfectly working against each other. One is as far up as the other is down. So the resultant displacement between the two is still going to be zero. So we see there's certain points that are always going to work together and certain points that are always going to work against each other. And that's what we're getting at here. Certain waves will work in phase, and certain points where they're always in an antiphase. Okay. And I've already kind of alluded to this, how the will have constant constructive or destructive interference. constructive if they're in phase, destructive if they're not in phase. Good, okay. So as a result, we have these fixed points. So let's find another one. We have these fixed points where the wave never moves because it's always destructive interference. So here's another one here. Fixed point where the wave is never going to move. There's going to be another one here where the wave is never going to move. And so the resultant from one wave going to the left and the other going to the right is this new effective wave that can't move left or right because it's stuck. And it's actually only going to move up and down instead. So the resultant wave is going to look like this. Now that looks pretty similar to before, but the point is that at a later time step, all this stuff oscillates up here and back down, all this stuff oscillates up here, back down, up and down. But there's no feeling that the wave is moving to the left or the right anymore. It's stuck. You just have these little oscillating sections. Good, okay, and this goes on forever. So da, 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 da. And this effect of a wave, an effective wave that doesn't seem to be moving, is what we call a stationary wave. Stationary because it doesn't seem to be moving. So the resultant wave only moves up and down. This is a stationary wave. Good. Okay, so that is stationary waves. So how are we feeling? Anyone got any questions at this point? One, nice, okay, good. Well, if there are any questions, let me know. I'll keep my eye on the chat. In the meantime, I'll get us started with some exam questions. So, figure 4 here represents a stationary wave formed on a steel string fixed at P and Q when it is plucked at its center. Okay, explain why a stationary wave is formed on this string. So there's something that we haven't talked about here, which is a kind of a classic thing, which is that when you pluck a string, so let's imagine I have some string. When you pluck it somehow, what you essentially do is you create two waves. Waves that go either side from where you plucked. So one is going to shoot off to the left, and the other is going to shoot off to the right from the point where you plucked the wave. Okay, and because you create those two waves, eventually those waves are going to hit the boundaries and return to each other. And then you have two waves, which are essentially the same, but in opposite directions. And that's going to create your stationary wave. This is a classic answer, and I'm just going to say it in more detail more slowly now. So plucking string causes two progressive waves to travel outwards. Okay. The waves that are produced reflect back on themselves on themselves at P and Q. P and Q are these boundaries. Okay. The waves are coherent, continuous, and in opposite directions. Directions. So generate a stationary wave. Remember, those were the conditions we needed. Coherent, continuous, opposite directions. Okay, very good. Next question. When a note is played on a violin, the sound it produces consists of the fundamental and many overtones. This is a really good question, by the way. Figure 8 shows the shape of the string for a stationary wave that corresponds to one of these overtones. The positions of maximum and zero displacement for one overtone are shown below. Okay, good. Points A and B are fixed. Points X, Y, and Z are points on the string. Describe the motion of point X. So continuous means it's not just a pulse. So in one slide, we're imagining just a little pulse of a wave, just a little lump of amplitude that's moving along, little lump of energy. However, by continuous, we mean a wave that actually looks like this. So this is like a piece of a continuous wave. So it's not continuous, but this goes on forever. This is a continuous wave. Okay. So let's zone in on point X. The key thing to understand here is that point X is just moving up and down. So point X moves up and down. And let's just say a bit more because there's 2 marks. Its displacement is smaller than points to the left and larger than points to the right. To the right. Why am I saying that? We'll look at this point here. This point above it is a point where the 2 waves that made the stationary wave are always working, let's say, more well together than at point X. There's this whole kind of spectrum between the point where they're always working perfectly together and the point where they're always working perfectly against each other. But this point X is always going to be working a bit better than points over here. So it's always going to have a bigger displacement no matter what time you're at. It's also always going to have less displacement than the point just to the left of it. Good, okay, and no problem at all. Okay, so now we're asked to state the phase relationship between X and Y and between X and Z. Okay, so this is a really good question. Now, something about this wave might lead you to think, if this was just a single wave, and you are thinking about this point X here, and this point Y down here, you might think, well, X is kind of high up, but it's not at the peak. Y is at the trough. So they're not in phase, but they're not in anti-phase. They're not at opposite points in their oscillation, right? Well, actually here they are. They're always, the point is that everything in this section here is moving up at the same time. It's just a load of points moving up and down. It's just that some are moving up and down with bigger amplitudes than others, giving you this weird stationary wave looking shape. And however, if X, for instance, were at the top of its rise here, Y would be at the bottom of its oscillation here. And in general, they're going to be at opposite points. X is going up at the same amount that Y is going down. So X and Y here are actually in anti-phase. They are at opposite points in their cycle, even if they don't really look like it. And that's one of these just weird things about stationary waves. Similarly, Z here is at a higher point in terms of distance than X. But they're both moving up together, just at different amplitudes. And they're both in phase at all times. So X and Z here are in phase. Good. So the point is, it's not a single wave. It's this weird stationary wave made by a pair of waves. Good. Okay. So now we're going to move on and discuss the properties of stationary waves. And someone asked about overtones before, and we might have some time to get to talking about that. But a precursor to talking about that is understanding harmonics. Okay, which in a sense are overtones, in fact. Okay. So to get there, first we're going to need to introduce just a little bit more terminology. It's still terminology about those stationary waves, though. And we're going to need to talk about nodes and antinodes. So we're going to say that a node is a point at which displacement is always zero. Okay. So if we look at the stationary wave, the classic points are going to be this point here, this point here, this point here, and so on. Those are nodes, points that always have zero displacement. Good. And then we have antinodes. Okay, an antinode is a point which always has a maximum displacement. A point which always has largest displacement. Okay, so here's an antinode, here's an antinode, here's an antinode. These are all antinodes. Good. The displacement of this point here is always going to be bigger than the displacement of this point here or the displacement of this point here. They're all going to move up. This might not be the top of the oscillation. They're all going to move up together and down together. But that one in the middle is always at any time going to be higher than the things to the left and the things to its right. Okay, good. So we've got nodes and antinodes down. Now let's talk about harmonics. So recall, this is a refresher, a stationary wave is formed on a string when a progressive wave, what's a progressive wave? Well, I'll write that in a second. Progressive wave is just one that is not stationary, one that does actually appear to be moving in some direction. The stationary wave is formed when you get one progressive wave and it is reflected back on itself. Good. Okay. Now, it turns out that you won't always get a nice stationary wave. You'll only get it when the wave you began with had a good or an ideal frequency. And those ideal frequencies that allow you to make stationary waves on some specific string are called harmonics of that piece of string. Good. So let's take a look at some examples of the harmonics, and we'll begin by talking about the fundamental harmonic, and that is actually what it gets called. It gets called the fundamental. So, okay, let's imagine I have my piece of string and it's fixed on two ends, this end here and this end here. Essentially, the biggest stationary wave I could fit on it is where you just have that this entire piece of string is moving up and down together, all coherently. Every point, if you like, is in phase at all times. Now, if you look at this picture, it doesn't look much like a wave. In fact, it looks like about half a wave. So in fact, you can think about this here as being half a wavelength. And you can say that this is the biggest possible wavelength that you can fit on the string. And you say that this is the case where the length of the string is equal to a half of the wavelength. That is one option. It is the largest wavelength that you can have. In other words, it's the smallest possible frequency that you can have. And this gets called the first harmonic. It's the first choice available to you. Okay. Now what we can do is just add in one more node. And we've added that one more node in the middle here. Now, if we look, it looks like we fitted a whole wave on the string. So in fact, the length of the string, sorry, I didn't say this. L I'm using to mean length of string. I don't think I actually said that. This time we have the length of the string again, and this time it's going to be equal to its whole wavelength. And here we've just added in yet another. The length of the string now, if you look at it, is equal to where we have half a wavelength, another half a wavelength, and one more half a wavelength. So it's 3 lots of half a wavelength. Good, okay, and these wavelengths that you can fit on the string are then called the second harmonic and the third harmonic, respectively. Third. There you go. And I think that's all we need to say there. Yeah. Okay, good. Right. So far I talked about the wavelengths, and now we're going to talk about the frequencies, which is usually when people talk about overtones. I think they're probably usually thinking more in terms of frequencies, but they're thinking in terms of pitch. Okay. So let's think about our string again. And I said there was a fundamental harmonic, and the frequency of the fundamental harmonic that is called, or the first harmonic, if you like, is called the fundamental frequency. Fine. And the fundamental frequency is a material property. If I have my piece of string and I know its length, and I know the tension in the string, in other words, how tight I've pulled it, and I know something about how dense it is, I know something about its mass per unit length, which I call mu. So mass per length, that's called mu. If you know all of these things, you can calculate this frequency. The frequency of the big wave you can fit where half a wavelength is the entire length of string. So this frequency is, and it's just a formula, you don't need to be able to derive it. This is the formula. Okay, so what's this formula telling us? Well, first of all, it's telling us if you increase the tension, you increase the frequency. Okay, so if you pull the string tighter, in some sense, it's naturally kind of higher pitched. Okay. If you ever tuned a guitar, this should sound familiar. If you want to make the guitar string sound higher pitched, you have to essentially stretch the string using a tuning peg. Okay, good. What else do we want to say? Well, any other harmonic frequency, for instance, the second harmonic or the third harmonic, those will all have frequencies which are whole number multiples of this fundamental frequency F0. Okay, so let's look at some examples. So remember in the first harmonic, the length of the string is the wavelength over 2. Actually, if we go back to this previous part, let's rearrange for the wavelength for a second. We had wavelength equals 2L. Here we had the wavelength equals 2L over 2. Here we have wavelength equals 2L over 3. And so you see a general formula here for the nth harmonic. The wavelength is equal to 2L over n. Now we're going to see that there's an even nicer formula for the frequency. Okay, so going back to the second harmonic, let's talk about the frequency. Remember, this is the case where lambda equals L. Okay. Now, for the second harmonic, it turns out that the frequency is simply just double the fundamental frequency. Okay, and since the fundamental frequency we have a formula for, we can say that the frequency is 1 over L square root of T over mu. Okay. Now, for the nth harmonic, the frequency is simply n times the fundamental frequency. Okay. And so in fact, we can just simply write it as n over 2l square root of t over mu. And that's what I think I want to say there. You can, in principle, deduce the frequency of the nth harmonic from the wavelength of the nth harmonic and vice versa. But okay. Good. So actually, we just about have some time, so I'm actually going to do that. Yeah, let's do a bit of bonus here. Okay. What's the speed of the wave in the second harmonic here? Well, the formula for speed is always frequency times wavelength. Here, the frequency is 2f0, and the wavelength is L. Okay. Now, something that I haven't mentioned here is that the speed is going to be the same, no matter what harmonic you're at. And because of that, you can use the frequency of the nth harmonic to rederive the formula for the wavelength of the nth harmonic. So for instance, we know that the wavelength of the nth harmonic is going to be, in general, the velocity, which is always the same, over the frequency of the nth harmonic. Now, the velocity, we already calculated it here, and it's going to be that no matter what. And then we simply divide by the frequency of the nth harmonic, which is actually n f0. And we get back to that formula again. We get 2L over n, which is just the formula that we got more concretely on the previous page. Lambda equals 2L over n. Good. So now you can just kind of see how these things are related. They're related because the speed is always the same on this string. Good. Okay, how are we feeling? Do we have any questions? Thinking about two, okay. Like I said, if you have any questions, feel free to ask them. Someone asked at some point about overtones. Okay, now I don't want to say things that aren't true. I don't remember properly exactly what people mean when they say overtones. But I think the overtones are just all of the harmonics that are not the fundamental harmonic. And the point is that when you pluck a real physical string, because physical strings are messy and they're not ideal, like in our science textbooks, they work in such a way that you kind of end up hearing. You don't just hear the one frequency, but you hear all these higher frequencies called like overtones as well. I think I can say anything deeper than that and just say that overtones are roughly higher harmonics. And I can't remember exactly how the terminology works. It probably doesn't really answer the question I had, but the person who wanted to know more about overtones, if you have like a more specific question, there's a chance I can say a bit more about it, but I also might be out of my depth, so we'll see. Okay, in the meantime, I'll start working us through some exam questions. Okay, so we have question 4 here. And figure 4 of question 4 says, we're looking at the side view of a string on a guitar. The string cannot move at either of the two bridges when it's vibrating. When vibrating in its fundamental mode, the frequency is 108 hertz. Okay, calculate the wavelength of the fundamental mode of vibration. Okay, well, what was our formula? In general, the wavelength is 2L over n. The fundamental, that's the case where n equals 1. So the wavelength should simply be equal to 2 times the length of the string. And the length of the string is 0.64. So it's 2 times 0.64, which is going to be 1.28. And that's measured in meters. Good. Next question. Calculate the speed of the progressive wave on this string. Well, speed is always equal to frequency times the wavelength. The frequency is 108 hertz. The wavelength we just calculated was 1.28. And if we put that into a calculator, we should find 138.24 meters per second. And so roughly two significant figures, since they only gave us oh no, they gave us three significant figures actually. So I think we can leave that as one. I needed 140, but actually I think 138 is better here. 138 meters per second. Two, three significant figures. Good. Okay. So is this continued? I think it is continued, yeah. While tuning the guitar, the guitarist produces an overtone. There we go, there's that word, overtone. So here they're just using overtone to literally mean harmonic that is not the fundamental. An overtone that has a node 0.16 meters from bridge A. And they've drawn it here, so let's actually draw the node already. Make sure we're digesting the question. Figure 5, sketch the stationary wave produced and label all nodes that are present. Well, there are actually many answers to this, but there's one that they're clearly aiming for us to go for. So I'll do that, and then I'll mention why this question is a little bit ambiguous at the end. So, okay, we want to draw a stationary wave, and we know there's always going to be a node where we're fixed, and there's another node here. They've told us that. So it's going to look like this. And then, presumably, we're just going to have to make all of these dots equidistant. So it's going to look like that, and like that. Good. Okay, and then we should draw the other half of the stationary wave as well. This is the standard way to draw it, to try and get across the idea that it's going up and down, but not left and right. So dotted line says where it was some time step ago. Fine, so there's our answer. And we're asked to label all the nodes. So we should label all the nodes. Node, 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 nodes, node, 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 node. Good. Finally, we're asked to calculate the frequency of this overtone. Okay, good. So what we need to ask ourselves is, what harmonic are we at? What is N? So there's a good question for everyone. What is N here? We know the frequency is always equal to N times the frequency of the initial harmonic. And we actually know that this is 108 already. But what's N? What harmonic are we at here? This live has been on for approximately 50 minutes. I think we're on the last question, actually. So yeah, what's N here? Are we at the second harmonic, the third harmonic, the fourth harmonic, the fifth harmonic, the sixth harmonic? What one are we on? Yeah, good. Absolutely right. We're at the fourth one. If you're ever not sure, then you can go back to drawing the first harmonic. And when you remember that the first harmonic looks like this half a wave, then you realize the second one looks like two chunks, the third one looks like three chunks. You realize it's just like how many of these half chunks is the number that you're at. So you're absolutely right. We're at the fourth harmonic. Good. So this is 4 times 108. I guess it's 462. 432. 432 hertz. That is a final answer. Okay, good. So that's really the end of the session. You should now be able to understand the concepts of phase and superposition. You should be able to describe how a stationary wave is formed, and you should be able to define the nodes and harmonics of a stationary wave. So good. So let me know if you have any questions for me. I'll be keeping an eye in the chat. And while I'm keeping an eye in the chat, I will mention a bit more about our seminars that are coming up shortly. But as I mentioned before, we have these A-level exam crash courses coming up. And so, yeah, I'm just going to go through this, but I'll be keeping an eye on the chat. So if you have any questions, please just let me know. So At the end of March, beginning of April, we have the A-level exam crash courses coming up. And I just said that we're going to focus on approximately 4 things, and I'm just going to talk a bit more in detail about how they're going to work here. So one of the key things, one of the really important things to focus on, especially towards the end of the year, is exam technique. You know a lot of stuff by now, but you still need to be able to tell the examiner the stuff that you know and be able to know what stuff the examiner wants you to tell them. And that is its own skill. And it's a skill that can be learned. Uh, so we'll teach you somewhat about exam technique skills, how to break down questions and interpret what the examiner wants. We'll teach you about the range of kind of classes of question types that come up in the exam. There is some amount of formula to the kinds of questions that you will be asked, from state, define, explain, plan, these common words that indicate the kind of answer you're going to have to give. And we'll give lots and lots of step-by-step examples to how we would answer exam questions throughout the day. Again, we'll give you that training through the medium of what we think are typically the topics that people find trickier in A-level and AS level physics. There is an associated booklet which essentially contains what we're going through during the day of the course. And there's various things to complete during the day. This is the thing that you can take home, and it has lots and lots of extra resources that we've made that won't be gone through the day, like lots of extra mocks exams and tests for your understanding as well. Finally, during the day, there'll be somebody presenting. And while here I was presenting and keeping an eye on the chat, on the day there'll be one person presenting and another person just watching the chat, just responding to the questions that anyone has about anything that's being presented. Okay. And here's just the details of the dates and where these courses are. You don't have to be there in person. You can also attend them via a live stream in Zoom. And those are the dates when they're running. And so if you have any questions about those, please let us know. Please let me know. There's a final page where you can find out more. And yeah, in the meantime, I'm just keeping an eye on the chat to see if there are any questions about today's session. Oh yeah, no problem. Thanks very much for coming, and thanks for your interaction in the chat. It's always super helpful, and I hope it was useful. Okay, so I'm not seeing any more questions in the chat. So I think at that point, we can leave it there. And I'll just say thanks again, everyone, for coming. It's a really enjoyable session. I hope it was useful for all of you. And I will catch you all at the next one. Okay, bye.